All right, we're going to find the critical points of this function, and then we're going to use the second derivative test to determine whether those critical points correspond to local maxima or local minima or neither. So first, we're going to locate critical points, and the way to find critical points of a function is we take the first derivative and we set that equal to 0, or we ask the question, where does that first derivative not exist? And before we get started, to avoid any confusion, I want to point something out about this function. I want to look at the domain of our function, and because our function has a natural log in it, that means that our x values cannot be 0 and they cannot be negative. So the domain of our original function here is 0 to infinity. So when we're looking for critical points, we're going to look for critical points on the domain of the original function. Okay, so let's find our critical points, and let's start with a first derivative. Note that this first term has a function of x multiplied by another function of x. So we're going to need to use the product rule to find this first derivative. That means copying down the first term, multiplying by the derivative of the second term, adding, writing down the derivative of the first term, and then multiplying that by the second term. So all of that is the product rule. The derivative of our second term, this 15x squared, is just going to be a power rule. We take the 2 times the 15 to get 30, and then we reduce the power on x by 1. All right, let's keep going with this derivative. The derivative of the natural log of x is 1 over x. The derivative of 2x squared is 4x by the power rule. Now we can cancel this x in the denominator with one of our x's in the numerator. That would leave us with a 2x term here. And we have a 2x minus a 30x. Those terms can be combined. Now we're going to be setting this first derivative equal to 0, so it's helpful if we can factor. So I'm going to take a factor of 4 and a factor of x out of each one of these two terms. And we have to ask the question, where does this first derivative not exist? And also, where is this first derivative equal to 0? Well, first of all, this first derivative does not exist at x equals 0 or for negative x values. However, recall that our domain is 0 to infinity. So we're not interested in critical points at x equals 0. As far as where this first derivative equals 0, we would split this up into two pieces. We would again go to critical point of x equals 0, but that's not on our domain, so we're not going to worry about that one. However, this factor here, solving for x means adding 7 to both sides, and we're going to exponentiate this equation again. That would get our x by itself, and we get an e to the 7th power equals x. Now, if you're wondering what happened between these two steps, what I did is I took the left-hand side of the equation and put it in the power of e, and I also took the right-hand side of the equation and put that in the power of e. The exponential function and the natural log function are inverses, so they cancel each other out. That just leaves us with an x on the left-hand side, and that just leaves us with an e to the 7th power on the right-hand side. So we did all of that work so that we could find a critical point, and our critical point is x equals e to the 7th power. Now we're asked to use the second derivative test to determine whether this critical point corresponds to a local max or a local min. Well, what the second derivative test says is this. If we have a critical point such that the first derivative at that critical point, which I'm calling c, equals 0, and our second derivative evaluated at that critical point is negative, then that critical point corresponds to a local maxima. However, if at this critical point the second derivative is positive, then that critical point corresponds to a local minimum. So in other words, what we need to do with this function is take a second derivative. I will start with this version of the first derivative right here. Again, that's a product of two functions. So I will write down the first and take a derivative of the second function. Then I'll take a derivative of the first function and copy down the second function. Now the derivative of the natural log of x is just 1 over x, and the derivative of 7 is 0. The derivative of 4x is 4. Doing one step of simplification and combining like terms gives us that our second derivative is 4 natural log of x minus 24. Now what we're going to do with that second derivative is we're going to plug our critical point into it. So we're going to replace x with e to the 7th. And if you recall that the natural log and exponential functions are inverses, you'll remember that they cancel with each other, leaving us with a 4 times 7 minus 24. That's 28 minus 24. That gives us an answer of 4. More importantly, this 4 is positive. So by our second derivative test, we had a critical point such that the first derivative was equal to 0 and the second derivative is positive. Then what that means is that the critical point that we found corresponds to a local minimum. So I'm going to make a little space and write that down. And okay, I think that's going to do it for that problem. I'll zoom out on the whole thing so that you can see all of the work that we did there. As always, feel free to go back, rewind, hit pause, rewatch as much as you need to until all of the steps make sense. And I'll see you in the next calculus problem of the day.